All right, let's talk about something we've all experienced. You drop a glass and it shatters into a million pieces, but you drop a tennis ball and it just bounces. Why is that? It seems so simple, but the answer is actually pretty fascinating, and it's hidden deep inside the materials themselves.
I mean, really think about it for a second. Your favorite ceramic coffee mug slips out of your hand and bam, it's gone. An absolute mess. But your kid's plastic action figure takes the same tumble and it's totally fine, not a scratch on it. They're both solid objects, right? So what in the world is the difference? Well, that's exactly what we're going to get into. You see, the whole secret to why some things break so easily isn't really about how strong they seem on the outside. Nope. The story actually starts with something you can't even see. Tiny, invisible weaknesses that are hiding in plain sight. That's right, Stacks. It turns out pretty much every material, no matter how perfectly smooth or flawless it looks, is riddled with microscopic imperfections. You can think of them as these little, tiny starter cracks just waiting for their moment. And these little guys are the starting point for almost every single break, snap, and shatter you've ever seen. So you might be thinking, okay, if everything is full of these tiny cracks, why isn't the whole world just crumbling around us? Great question. And the answer is a very cool property called fracture toughness. The best way to think about it is like a material's own personal superpower. It's the ability to see a tiny crack starting to spread and just stop it dead in its tracks. Here's a super easy way to see this in action. Grab a piece of paper. If you just pull on it from the edges, it's actually pretty strong, right? But now, make one tiny little tear on the side first. All of a sudden, you can rip it apart with almost no effort at all. Why? Because all that pulling force you're applying gets focused. It gets concentrated right at the very tip of that tiny tear. The exact same thing happens inside materials, and fracture toughness is what fights back against that super focused force. Okay, so if these invisible little cracks are the key to everything, how on earth do scientists actually study them? Well, you might be surprised to hear this, but they don't just sit around and wait for something to break. Nope, they actually make a crack themselves, on purpose. You heard me right. They take a perfectly good piece of material and very carefully cut a tiny, precise little notch into it. This gives them a standardized crack to work with. This way, they're not just guessing about some random flaw inside the material, they're setting up a controlled experiment where they know exactly where the weakness is so they can see precisely how the material handles it. So they take this notched sample and they put it into a special machine that applies a really slow, really steady pull. They're not trying to smash it or anything, they're just carefully increasing the force bit by bit, all while watching that little pre-made crack like a hawk. And the exact moment that crack starts to grow, they measure how much force it took. That number they get is called Kc, and it's the direct measure of that material's fracture toughness. The higher the number, the tougher the material. It's all about seeing how it holds up under slow, predictable pressure. But wait a minute, in real life, things don't usually break from a slow, steady pull, do they? Life is full of bumps, drops, and sudden shocks. So what happens then? Well, that changes the game completely. Let's go back to our poor coffee mug. When it fell, it wasn't a slow pull. It was a fast, sudden, hard impact. And this is where things get interesting. A material that seems really tough when you pull on it slowly might act totally different, way more brittle, when it gets hit hard and fast. And that means we need a whole new way to measure it. And that brings us to our second big idea, impact strength. So while fracture toughness was all about resisting a crack that's already there, impact strength is all about how much raw energy a material can soak up from a sudden hit before it finally breaks. It's not about resisting a crack, it's about surviving a shock. And the test they use for this is just brilliant. It's called the Sharpie Impact Test. Picture this. You've got a giant, super heavy pendulum. They lift this thing way up high. Then, they place a small sample of the material, which also has a little notch in it, right in the pendulum's path at the very bottom. And then, they just let it go. The pendulum swings down, wham! It smashes right through the sample. But here's the really clever part. After breaking the sample, the pendulum keeps swinging up the other side, but it never reaches the same height it started from. And that difference in height tells you exactly how much energy the sample absorbed when it broke. It's simple, powerful, and honestly, a little bit dramatic.
All right, so we've got these two different ways of looking at why things break. We have fracture toughness, which is for those slow, steady forces, and we have impact strength for all the sudden hits. Let's put them side by side to really lock in the difference and see why we need both.
So, on one hand, fracture toughness is what we'd call a fundamental property. It tells us about the material's basic, built-in ability to stop a crack. Impact strength, on the other hand, is a much more practical test. It tells us how that material is going to perform out in the real world when it gets dropped or banged around. Think of it this way. For something like a bridge, where the forces are constant and steady, engineers care a ton about fracture toughness. But for a car bumper or a case for your phone, impact strength is what really matters. And here is a perfect, maybe slightly unexpected, real-world example from the source material: dentures. I mean, you definitely don't want those to shatter if you accidentally drop them in the sink. That's why impact strength is such a critical property when they're being designed. It's all about planning for life's little oops moments. So, is there a way to see all this at a single glance? Can you just look at something and know a material's whole story? Well, in a way, yes. Scientists have a tool for this. It's like a personality profile for a material, and it's all on a simple graph. Now, this is called a stress-strain graph. I know, it sounds a little complicated, but it's not, I promise. It's really just a picture, a visual story of what happens when you pull on a material until it finally breaks. The shape of the line on that graph tells you everything you need to know about whether it's tough or brittle. For a brittle material, like our ceramic mug, the graph tells a really short and violent story. The line just shoots straight up and then snap. It just stops. Dead. There's no warning, no bending, just a sudden catastrophic failure. But for a tough material, like a piece of plastic, the story is much longer. The line was up, and then it starts to curve. That curve shows the material is stretching, it's deforming, it's absorbing a whole lot of energy before it finally gives way. It bends before it breaks, which is a pretty clear warning that it's under a lot of stress. So, next time you pick something up, your phone, the chair you're on, anything, just take a second to think about it. The glass screen on your phone, that's a perfect example of a brittle material. But the case you put around it to protect it, that's designed for toughness and high impact strength. The world all around you is just this constant dance between these two incredible properties. And now you know the hidden science that decides why things bend and why they break.